My name is Ian Lawson. I'm a senior naval architect with Bristol Harbor Group in Bristol, Rhode Island. I'm here with Greg Beers, principal naval architect at Bristol Harbor Group. And now you may be looking at this title slide and wondering if we didn't show up to quite the right conference, but I want to approach sustainability from a little bit of a different angle. The previous presentations we've heard here are really exciting and I think are describing a future we all want to live in. And until we get there, this presentation is about making sure the lights stay on and you can charge your electric car and your electric boat every day until that point. So we're very excited to get to a point where we can electrify everything, and we think this is an important piece of how to get there. So, as an introduction, we mentioned this presentation is about developing a fleet of Jones Act LNG carriers. The Jones Act, for anyone who might not be aware, is the current US policy that requires that any vessel that carries cargo, commercial cargo, from one US port to another US port must be built in the US and flagged in the US, among other things. And currently, there are no Jones Act LNG carriers. So, as the US power grid is adding renewable capacity, there is currently and still will be for the foreseeable future on the scale of the lifetime of a marine asset, for example, a significant need, a critical need nationally for natural gas to keep our current services running, and as we'll discuss a little bit later in the presentation, to complement renewable energy as it comes online. With that being the case, the transportation infrastructure for that natural gas, primarily LNG carriers and pipeline, are essential for economic and energy security. And we argue that the US needs a state-of-the-art fleet of Jones Act LNG carriers, and further that the government needs to support the establishment of this fleet in order to promote sustainable American energy. So, what are the benefits of developing this fleet of Jones Act LNG carriers? First of all, we want to improve and maximize the sustainability of the baseload and standby power grid. As I'm sure everyone is aware, renewable energy, especially at a small scale as it's being introduced into a new region, comes with weather dependence and variability. And as that introduction of the renewable resources such as wind and solar grow, that variability can also grow in scale. So as we currently do, there are other resources in the energy mix to make up the difference between the electric demand curve and the supply curve coming from renewable resources. While we have that delta, that need for baseload or standby power, we want to make sure that's as efficient and responsive as possible. And natural gas power plants are a good fit and balance for those needs. The energy security is a priority that we want to keep in mind. And by ensuring the resiliency and the reliability of the power grid during the renewable scale-up, we need to be able to maintain energy security as well as economic security. We also believe that developing a fleet of Jones Act LNG carriers will help revitalize the commercial shipbuilding industry and introduce scale-up in new supply chains and supply chains that are going to be really critical down the road as well for developing transportation infrastructure for future fuels. So, what problems does the Jones Act fleet solve? There's an environmental strategic problem. As renewable energy gets added, we need to make sure we have dispatchable power that can handle the fluctuations. And this actually pairs really well with the goals of renewable energy especially in being able to replace older, more polluting power generation technologies such as coal-fired power plants and oil-fired power plants. So where those power plants may not be as readily able to handle the variability from wind and solar as it starts to come online, there's an incentive to replace those power plants with more efficient and much more flexible and easily scalable natural gas power plants, combined cycle, the highest efficiency fossil fuel power plants we have. So those natural gas power plants are required to, at least in the near future, to provide that standby power. And LNG carriers specifically have some benefits that also complement the renewable energy. So first of all, the LNG carriers are very flexible, and where we want to start building up renewable energy or shut down a coal-fired power plant somewhere that is not currently served by a natural gas pipeline, an LNG carrier can fill that hole. Additionally, LNG carriers are very efficient. They can use their own boil-off gas as fuel and use natural gas as a relatively efficient marine fuel. And the technologies, as we mentioned, that go into a state-of-the-art LNG carrier are solving a lot of the same problems that need to be solved to carry other things such as hydrogen or other e-fuels that we expect may scale up significantly and become a larger part of the transportation economy in the future. In addition to the environmental side, there are some major domestic strategic problems that LNG carriers, specifically Jones Act LNG carriers, solve. As you may or may not be aware, there are regions in the United States, for example, New England, that are currently highly dependent on natural gas for power and heating. And the pipelines that currently serve those regions are unable to fully meet the demand that they have. So, surprisingly as it might be, as the United States is a major producer and exporter of natural gas, New England has to regularly purchase foreign natural gas delivered on foreign LNG carriers to meet their total demand every year. And this is just one example of areas where the lack of the Jones Act vessel means we cannot transport our own product to our own region, because that would be carrying it between two US ports. And there's only foreign vessels that have the technology to do that currently. There are other examples such as Puerto Rico and Hawaii that also have similar gaps in the energy supply infrastructure. Additionally, even where there is not currently energy insecurity in a region that is adequately served by pipelines, there is always the potential for a pipeline to become inoperable for one reason or another. And we've seen this happen. And by having a secondary asset that is not subject to the same vulnerabilities, LNG carriers can be a virtual pipeline to make sure those areas stay supplied with critical energy while they still need it. Broadening scope a little bit, there is also an international strategic angle to this. The US has various allies that we supply with natural gas that are pursuing the same goals, trying to scale up renewables, trying to replace coal power plants, and overall just currently being heavily reliant on natural gas. And without full ownership of the vessels that transport our domestic product to these allies, there is always a vulnerability for some third party in the supply chain with differing national interests to be able to make that a problem for us and either exploit this vulnerability or otherwise act in a way that limits our ability to supply domestic products to our allies. A Jones Act fleet of LNG carriers would mean that that transportation capability is fully under our control and eliminates that vulnerability. So if I've at all convinced anyone that the usefulness of LNG carriers is there and they provide complementary benefits to sustainable energy, you may ask, why do we not currently have a fleet of Jones Act LNG carriers? And right now, while we have built them in the past, it has been decades since the US produced an LNG carrier, and our technical capabilities in shipyards have fallen behind, and the regulatory pathways, the regulations that exist that we would need to follow are very out of date and have fallen out of step with international standards. Someone else mentioned the struggles with groundbreaking regulatory territory with the Coast Guard. That's a huge issue with LNG carriers, to the point where there's some almost prohibitive regulatory challenges, and some have even been recommended to just go with a simpler asset, such as an LNG carrying barge, rather than try to create a proper self-propelled LNG carrying vessel. Additionally, there has previously been concern of whether the market would support the massive risk that shippers would need to undertake in order to invest in developing this capability. However, we believe as markets shift, there is an opportunity and a path forward right now to develop this capability in the United States. And to go into that in more detail, I will hand it over to Greg.
All right, thank you, Ian. As Ian said, I'm Greg Beers. I'm a principal naval architect with Bristol Harbor Group. And Ian has done a great job introducing the problem and relating it to the renewable energy sector. So with the need well understood, we can turn our attention to the solution. And although we've mentioned some obstacles, and I'm going to talk about a few more risks and mitigations, the solution is fairly simple, and we are uniquely qualified to discuss it as we champion the first LNG membrane barge through the Coast Guard back in 2018. It took us over 4 years. So step one is to develop the U.S. capability to produce a small, say 12 to 17 or 15 or 12 to 20K, that's 1,000 cubic meters, sticking with the metric system here, of LNG barge. So the idea is that we need to be able to produce a 12K membrane style barge. Why membrane? Because the membrane technology for carrying LNG is the only scalable, not only, is the readily used scalable option. Type C tanks, which are pressurized tanks that you've seen on many vessels, they can only be built so big, but a membrane vessel can be built to carry industrial scale. So first thing we have to do is build some small those have been built. In addition, we need to have built a membrane tank vessel. As I said, the Clean Jacksonville, that's the vessel that we shepherded through, has been built. And currently, just recently, a 12K Type C LNG barge was delivered, Jones Act barge was delivered. So putting the chocolate with the peanut butter, putting it all together, you can see that a 12K membrane style barge can be built domestically in our shipyards now. So step one is complete. The second step is to develop the U.S. capability to produce a small 12 to 20K membrane style LNG carrier. So the difference here is it's not a tug and barge, it's not an articulated tug barge combination. It is a carrier that can actually burn off its own boil off instead of using diesel to create energy that is then used to reliquefy the natural gas, as is done on ATVs. So the carrier is required because, as I said, it can be scaled. An ATV cannot. In addition, the first domestic, keeping the size of the first domestic LNG carrier the same size as the LNG ATVs and barges that are being built currently reduces the construction risk from the shipyard. So the shipyards don't have any construction risk. They know they can build this thing. It's simply taking the engine room from the tugboat that they're currently building and sticking it together with the barge that they're currently building. However, there is a large regulatory challenge associated with producing an actual carrier as opposed to an articulated tug barge, and that is what needs to be mitigated, and what is a chief point of our paper. And as I mentioned, as an example, getting that first membrane-style barge through the Coast Guard and ABS process took over 4 years. So to aid in this second step at Bristol Harbor Group, we have already produced a concept level design. You can see an arrangement plan of it here. And you've seen several graphics in the presentation to date. Those are all of that it's a 12K concept. But a full functional design needs to be developed and pushed through the regulatory process to mitigate that risk. Once that's done, once step 2 is done, and that regulatory risk has been removed, then the shipyards can look to building a large 174K or more industrial size membrane style LNG carrier. The only risk that the yards will have at this point is the scale and size of the vessel. So really tier 1 yards are going to be needed to build this. However, those tier 1 yards can utilize the industrial or the supplier base and the skills of the trades people that have built the 12Ks and 20Ks to build the components and the tank or tanks that will be needed for the 174K. And that's especially important because it also keeps those skilled tradespeople involved in the project all the way through to the full 174K vessel size. In addition, mariners can be trained on the smaller vessels and ported over to the larger vessels. We currently don't have a large pool of merchant mariners who operate domestically here in the US that operate LNG carriers. So to look a little more carefully at some of these risks, there's a primary commercial risk, and we're proposing a mitigation. Back in 2015, this whole concept was raised by lawmakers, and they looked to punitive trade regulations to try to force a fleet of Jones Act LNG carriers to be developed. They basically said XX% of domestic LNG must be transported on so many percent of US bottoms, right? The Jones Act vessels. That didn't work. That didn't happen. And commercial prospects, as Ian was alluding to earlier today, are significantly improved from where they were in 2015. There are many people, many countries that are interested in US LNG as well as other domestic regions here in the US that would like to utilize our natural gas that we produce. So given the recent shift away from Russia and the disruption to the European pipelines, there continues to be an exceptional demand for new export contracts. This paper proposes direct government subsidy to pay for the development of these designs and to aid in the construction of these designs domestically, as well as the crewing for these vessels, as opposed to these punitive trade regulations. As mentioned earlier, another primary risk is the regulatory risk. So there's significant regulatory risk to getting that first smaller LNG carrier through the regulatory process. And it will be challenging, and it is commercially prohibitive for some company to take that risk. So it needs to be pushed through with government support and aid. At the end of the day, this needs to be shepherded through the process with the support of the U.S. government. That's from our experience on the last one we tried to push through, or we did push through. So the mitigation is that subsidy, and the goal is to give that commercial entity the confidence that they can actually have this vessel designed and produced domestically. Another risk is the construction risk. So with that regulatory risk mitigated, as noted, the commercial there remains a commercial risk to the manufacturer, to the shipyard. However, as I mentioned earlier, the infrastructure that is developed with the smaller 12 and 20K vessels can be utilized to mitigate that risk for these tier 1 shipyards that aren't currently building membrane style LNG carriers. So basically, the risky technological leap that they need to make can be mitigated by utilizing either the same people, or to utilize those people to train. This also serves to broaden the industrial base, which there's been much talk about lately about the problems with the domestic shipbuilding and industrial base. And then there's the crew training risk that I mentioned, I alluded to earlier. So the U.S. does not have a large pool of mariners trained to operate these very complex vessels. One of the reasons that ATVs are utilized is that they require less crew and crew with less credentials. So we do not have a large group of domestic U.S. mariners capable of operating a 174K LNG carrier. So a mitigation is noted, and it's described much more depth in the paper, but as an integral part of step 2 is to design those initial vessels to oversize their accommodations and to plan to use them as training ships. So they'll have additional berthing and be able to serve as the training vessels for the crews for the larger vessels. The operators will need support to help cover those costs. Of course, that's part of the subsidy we mentioned. And to maximize the benefits of this, maritime academies and seafarer unions can be engaged to help develop the curriculum and place cadets and apprentices on the smaller vessels, all building towards that pool of larger for the larger vessels. So, in conclusion, the point of this paper is to say there's a need for domestic LNG carriers to support our renewable energy goals here in this country. It needs to be a carrier versus an articulated tug barge or any other kind of barge-based vessel because it's more efficient and it's faster. And being faster is really interesting because that can open additional trade routes, say through the Gulf of Mexico, even down to Mexico, or Brazil is one of the largest importers of domestic U.S. LNG currently. The smaller vessels that we talked about that would be used as training vessels and to develop the capabilities here domestically in our shipyards and with our designers and the engineers can find service immediately as bunker vessels. There's a great need for LNG bunker vessels domestically, and an LNG carrier, as opposed to a barge, is able to accomplish that mission more efficiently than can the barge. In addition, the LNG carriers, the large industrial scale, can provide a virtual pipeline to help with all sorts of issues and to dispatch that energy as needed to support the development of the renewable energy grid in this country. And developing a fleet of LNGCs designed in the U.S. can aid in the development of the U.S. industrial capacity because these are technologically advanced vessels. They are more akin to a rocket ship than they are to an oil tanker. Okay, so this is really high-end engineering, high-end manufacturing that this country is capable of, but needs to develop it and develop that capability in a logical sequence. And this paper presents a stepwise plan to accomplish just that. So that's it. And I want to say thank you so much to Webb and to everybody for this opportunity.
We have a couple of minutes for questions.
Thank you for a very interesting, relevant presentation. You didn't discuss the exact containment system. And how is that related to building in the US? You probably need to license it from GTT or another.
Yep. So the 2.5K that we designed utilized GTT's Flex 3 membrane system. So that is the baseline for what we're assuming at this point. But no plugs. We're not working for GTT or anything. But that is certainly what we would assume would be utilized. Yes.
And you were allowed within the Jones Act to import the technology.
Absolutely. Yes. Yep. That was done on that 2.2K. Yep. And same thing. We went through the training of those shipyard personnel to be able to weld 1.2 millimeter stainless steel containment system and all the rest of what goes along with that successful. That really wasn't that wasn't the problem, shall we say. That was accomplishable, but you want to be able to use that talent all the way through the whole supply chain. Yes.
Given that the U.S. was, first of all, the U.S. it should be known by this audience that the U.S. was the first country to build an LNG ship. We built it in Louisiana in 1950. It was an export order. So we have a tradition in this country of being a leader. Many people come back to that. Now, in the 1970s, General Dynamics shipyard built, I think, 10 or 12 LNG ships. Has the regulatory environment changed so much that none of that can be carried forward to your question?
No, none of it. But I can, like, a specific example I can give is the seats on the valves for the relief valves by regulation have to be stainless steel. Not made today, 100% composite. You can't buy that. That was several months of my life getting that through Coast Guard. Just doesn't exist. Another example, Zone 0 in the cargo handling room. Rest of the world considers it a Zone 1 where you can have explosion-proof equipment and the like. By our regulations, as they currently stood, as they did with the Aquarius and the vessels that General Dynamics built, that is a Zone 0 space. It is the equivalent of inside of a cryogenic pipe. You can't even have a light, you can't have anything in that space. These were just a couple of examples of the challenges. And I haven't done it yet for the carrier, but it has been very clearly implied that there will be that on steroids for trying to get a carrier. Yes.
It's very, very interesting. Is your goal mostly to be able to build the 177K LNG carrier in the US like the way it exists right now? Or are you also looking at helping the government lay out a plan for hydrogen shipping, ammonia shipping, all these other gases that might be around the horizon?
Excellent point. I'll let Ian answer that one. The answer is yes, but I'll let Ian answer it more succinctly.
Yeah. I think it goes hand in hand. A lot of the technologies that we're talking about, skilling up the industrial base and the manufacturing base, a lot of those technologies are directly or indirectly transferable. We're solving the same problems. We're trying to liquefy a gas. We're trying to contain it. We're trying to manage the thermal stresses and everything. So we do believe that there's a major boost to the readiness to producing those future e-fuel vessels from being able to produce a modern LNG vessel today.
Especially with the membrane system.
Thank you very much.
Thank you.